So before I move into evaluation matrices as well as the results, let us summarize what we have talked about the methods in terms of multi-target problem. And therefore, let's take a look at this one. The first one, independent classifier, indicating that, say now we have 4 labels we want to predict. In our Y example, we have 3 labels that we want to predict. This is the most basic one. We use the attributes to build a classifier, say SVM, with the first label. We then use classifier to build a model to predict the second label, and we use the attributes to predict the third label. Then we have 3 independent ones, and we predict one by one without any connections with each other. The second method we discuss is power set. It's not shown in this figure. So what I'm trying to do is that we create the all possible labels, saying that if we have 3 labels, each one of them are binary, then we have 8 different combinations. So what we do is that we build one classifier, taking the attribute and then predict all 8 classes. And that is what we call a power set. The next one is the classifier chain. So what they're trying to do is that we use one SVM, train the attributes to predict the first label. We then use the attributes plus the first label to train the SVM for the second label. And then the third training would be including the attributes with the first label and the second label to predict the third label. So that is what we call a classifier chain. For the Bayesian classifier chain, as you can see in the figure now, depending on how we want to link them together, so this is something we need to design in advance, saying that we use this as the example. We use the attributes to predict the first label, and then we use the attribute plus the first label to predict the second label. And then in the third label prediction-wise, we use attribute plus the second label to predict the third label. So we need to design this before we move into the training. Of course, the network, conditional dependency network, is the most complicated one. We then need to use all of the other things to predict the label, and then we need to do that multiple trainings and then try to assign the best weight in each connections, and hopefully we can generate better results. So those is how the methods being used to build a classifier and then make the predictions. So now let's take a look at the evaluation metrics. I pick up 2 of the most important evaluation metrics specified in the multi-target problem to discuss, and so that is what we want to take a look. 2 of them. One is called Hamming loss, the other one is called 0-1 loss. Hamming loss is an interesting one that take the multi-target problem. We try to see how many of the predictions, since we predict multiple labels, we want to see how many of those are correctly predicted. And then for the 0-1 loss is more strict one, saying that we have 3 labels, only all 3 labels predictions are correct, then we consider it's a success. Otherwise, it's a loss. So you can see that by the 2 evaluation matrices names, they are all called loss. So what I'm trying to see is that the lower the loss, which close to 0, the better. If they are closer to 1, that means they lost a lot of the information. So let's take a look at the Hamming loss first. For multi-label classification, a misclassification is no longer a hard right or wrong. A prediction contains a subset of actual classes should be considered better than a prediction that contains none of them. So saying that there are 3 labels for the prediction, if we predict 2 of them correctly, it's better than predict 1 of them correctly. So let's take a look at this. And by looking into the formula over here, D is indicating the number of the testing data set. So obviously, if we have 10 testing data set, we need to look into one by one. And we try to see how many of those are predicted correctly and how many of them are not correctly. So what we're trying to do is that we look into the observations in D versus the predict label set in the observation in D. So what I'm trying to say is that we try to look into the prediction versus the actual value. That's what we call observation. How many of those are considered correctly? So we have the values. We try to see how many of those are predict correctly. And then if they are predict correctly, we get a value of 0. If they are different from each other in terms of 0, 1 or 1, 0, then that is what we consider as a 1. And therefore, the delta or the triangle over here is what we call XOR. And then what we will need to do is after we see how many of those are predicted incorrectly, we want to divide it by how many labels that we are looking at in total. So once we have looked into every single one of our testing data set, we sum them up, divided by how many testing data set that we have, and that is our Hamming loss. Of course, usually what I like to do is giving you an example. So let's take a look at this. So for example, we have 4 wines in the testing data set. The true label for the 4 wines are 010, 011, 101, 001. We can simply think as the region as the first label, grade as the second label, and the third label can be the price. So it can be the old world 90 plus and $29 below. So that's the idea of what we're looking at. Of course, if we're simply looking into the evaluation metrics, we just look into the numbers and saying that this is the true labels for the wines that we have. Saying that these are the predictions that we have. So you can see the first one, it predict the region correctly, it predict the grade correctly, but it did not predict the price correctly. The second one predict everything perfectly. The third one, everything is in the opposite, and the last one is missing 1. So saying now we want to calculate the Hamming loss, think about what is the values going to be. Let's take a look at this. So when we try to calculate the Hamming loss, basically we try to see that how many of those are incorrectly predicted, because remember, this is we consider as Hamming loss, which if we get a 1, that means it's a bad thing, and we use the XOR. So you can see that 0 XOR 0 is 0, 1 XOR 1 is 0. 0 XOR 1 is 1. So we have a 1 for the first testing data set. We have a 0 for the second testing data set. We end up 3 with the third testing data set because all 3 of those are predicted incorrectly. And then we have a 1 over here. So that you can see that for all the 4 testing data sets, we have these are considered as the loss value divided, since we have 3 labels, so divided by 3, and then we need to divide it by 4 because we have 4 testing data set. So the Hamming loss for this specific example is 0.416. So this is what we call the Hamming loss. Of course, the lower the better, we consider its value of the loss over here. The next one is 0.1 loss. This is more strict way of evaluating your predictions. So you need to predict basically everything correctly to get a 0. If you have 1 label incorrect, then it is a 1. It's a loss. So for observation, this measure compares the both predict label set and true label set. If they are not exactly matched, the loss for the observation is 1. And if they are exactly matched, the loss is 0. And therefore, you can see that this is a simply 1 or 0 evaluation. So in using the similar examples that we have, you can see that we have the same observation, the true label versus the predict label, and then we only have 1 of that is fully predict correctly. So we get a 0 over here, we get a 1 for the first testing data set, third and fourth testing data set, and since there are 4 testing data sets, we have all 3 losses divided by 4, so the 0.1 loss is 0.75. This is a much stricter way to evaluation the results. So the 2 evaluation matrices are the major evaluations that we use for the multi-target problems. And therefore, it is time for us to take a look at the results, how these things perform. So you can see that this is the table that lists out all the methods that we have discussed, starting with the single label. That is what we have done in previous chapter, I think chapter 5, looking into the prediction of the grade, price, and region, and we use SVM. We actually tried 5 different kernels, but we found out there are only 2 kernels that worth reporting, so we include those results over here. So this is what we done previously, which is not being considered as the multi-class, multi-label. We just put it over here to look into the binary relevance. So you can see that the 2 values are almost the same over here. And then what we're trying to do, the next one, is the label power set, which is the one that we have generate all possible classes. And we try to look into their grade, price, and region predictions. And of course, if we consider the Hamming loss and 0-1 loss, you can see that the label power set is actually performs better than others, because we do have some informations being included in terms of the labels. Then we look into the next 2 is the classifier chain and another classifier chain. Remember, if we look into the classifier chains, the order of the labels are important, since we can predict grade as well as region in a much higher prediction accuracy. So you can see that something is the 85%, 84%, and therefore we put grade and region in the front. So those are the 2 important things that we want to test out first. And you can see that the one that we reported over here is we're starting using the grade as the first classifier, first label to predict, and we use that information to predict the price, and then we use that to predict the region. On the other side, we use the region as the first one, predicting the grade, predicting the price. And therefore, you can see that if we compare the 2, they are almost identical. And if we consider the Hamming loss as well as the 0-1 loss, 0-1 loss are exactly the same. The classifier chain on this one has slightly better than the second choice. However, if we try to compare the classifier chain with the label power set, you can see that the label power set is actually performed better in terms of Hamming loss as well as the 0-1 loss. Finally, if we look into the basing as well as the conditional dependencies, this indicating that not all the labels are related to each other. We can design our connections as well as the probabilities of each one. You can see that these are the results that we can get, and actually the basing classifier is actually generating pretty solid results. However, compare with the Hamming loss with the label power set is actually performs better. And before I move on to the next slide, I want to mention all the results over here is using multi-label binary classes, indicating that each class for the grade as well as for the price are binary. So they are simply predicting for the grade is 90 plus, 90 minus, $29 above, $29 below, and the region is old world or new world. So this, of course, is considering a multi-label classification, which compared with multi-target classification, this is considered a slightly easier problem. So region tends to be the easiest label to do the prediction. It has a higher accuracy compared with others. Wine quality is similar to region, although a bit more challenging for the multi-label prediction. Wine price, of course, is the hardest one. We have discussed about this before. The attributes is actually talking about the wine testing, but it is not strictly related to the price, because when you read the wine reviews, wine reviewers write those reviews, define those attributes, which is closely related to the grade, because that's wine reviewers' grade. For the price, is that wine reviewers drink the wine, write out its reviews, give its grade, but the price is defined by the winemakers, and they are 2 different peoples, and that's why it's usually it can be explained why it is more difficult to make the prediction. So despite the single label besting most other approaches, the label power set in this multi-label classification is actually performs the best. Now, if we look into the multi-target problem, in this case, in the multi-target problem, now we are using the same different methods over here, and for the grade, we have 4 classes: 80 to 84, 85 to 89, 90 to 94, and 95 plus. For the price, it's going to be between $0 to $18, 18 to 29, 29 to 50, and 50 above. Region is still stays in the 2 regions. So if we look into that one, we have similar observations compared with the first 3 values. They are similar for the single as well as the class relevance. While we're looking into the label power sets, you can see that it's actually doing super bad in the price, and that's why it results in a much higher Hamming loss as well as the 0-1 loss. You can see it's actually doing pretty bad in terms of 0-1 loss over here. If we look into the classifier, compared with these 2, they are almost identical with the almost identical values in terms of the Hamming loss as well as the 0-1 loss. For the Bayesian network as well as the conditional dependency networks, they are actually predicts slightly better, especially the Bayesian classifier. It has 75% accuracy in the grade. In terms of the 4 classes, 75% is actually a very high results. For the price, it has about 47%, and for the region, it's about 84%. So that the Bayesian classifier seems outperform all other methods in this multi-target classification. So while most algorithms are able to tie this performance in grade and region the same, it is not the same for the price. In our case, Bayesian classifier chain is the best in terms of the price part, and that's why it has a better Hamming loss compared with the other methods. So finally, we look into a comparison with the multi-label problem versus the multi-class problem. So that is some summaries of what we can see. Basically, we have looked into the values over there. This trying to say that the label power set is better in terms of the multi-label by classes problem, while we have a multi-target problem. The Bayesian classifier chain seems doing a better work over here. So that summarizes everything in chapter 7 of the multi-target problems in Wineinformatics. So it is time to let us take a look at the assignment. So the assignment is pretty simple, saying that we have 6 lines, and we have the true labels listed over here, while we have predict labels over here. So I want you to tell me what is the Hamming loss value and what is the 0-1 loss value. So please submit this through the Blackboard. This is a simple practice, and I hope you enjoy reading probably the most important chapter of this thesis. The last slide is about some possible future works. This is interesting algorithms I want to discuss about probably in the near future. Multi-label k-nearest neighbor. So we all know what is the k-nearest neighbor already. How do we adapt that concept into the multi-label problem? That summarizes everything I want to discuss in this chapter.